Recognizing and using fundamental identities means first knowing what an identity is. An identity is an equation, but it's a very special kind of an equation. Here's an equation, 3x plus 2 equals 7. I can solve this equation for x. In other words, I can find out what value of x makes this true by using inverse arithmetic. X has to equal 5/3. I can check whether it's true by replacing the x with the value I found, checking to see if it's true. 5 plus 2 does in fact equal 7. That's an equation. Here's an identity. Sine squared t plus cosine squared t equals 1. The difference is that there is nothing to solve here. This is always true. What I might be asked to do at some point is to prove that it's always true. For right now, it's just important to note that the difference between this equation and this equation is that this one can be solved for the one value of x, where is it, that makes it true. This one cannot be solved for the one value of t that makes it true, because there is not only one value of t. It's true for every t. Remember that sine was just y, and cosine was just x, and r was just the radius of the circle. That's just the Pythagorean theorem. So this is a very minimal proof, but I've just, kind of demonstrated that this identity is true, right? I haven't solved anything, and that's the difference. So let's take a look at some of the identities we already know. We defined tangent of t as y over x. Well, y is the sine of t, and x is the cosine of t. So here's an identity. The tangent of t equals the sine of t over the cosine of t. This is true no matter what t is. There's not one solution. Any angle will work, right? So this is an identity. Here's another one. The cotangent of t was defined to be 1 over the tangent of t. Well, the tangent of t is the sine of t over the cosine. And if I write 1 as 1 over 1, that gives me 1 over 1, not divided by, but times the reciprocal, cosine of t over sine of t. So therefore, the cotangent is cosine of t over the sine of t. That's another identity. It's true for every value of t. The secant of t, we defined that to be 1 over cosine of t. And the cosecant of t is defined as 1 over the sine. So if we know the sine, we can flip it over to get the cosecant. Or if we know the cosecant, we can flip it over to get the sine of the same angle. But this identity is always true because it's defined that way. As it turns out, it's more than just the definition, but we don't quite have the tools we need for me to demonstrate why that's the case. We'll be learning about that in the next section, section 5.4. For now, what I want you to know is that you already know these 4 identities. They are identities, not just generic equations. There's nothing to solve there. And we're going to be able to use these to evaluate functions, to evaluate trigonometric functions at certain values. And we're also going to be able to use them to simplify trigonometric expressions. So those are the 2 other things we need to do in this video. Let's start with evaluations. Let's evaluate the tangent of pi over 4. Now, we don't know what the tangent of pi over 4 is just outright, but we know what the tangent of any angle is. It's the sine over the cosine of that same angle. So I can write this as the tangent of pi over 4 is equal to the sine of pi over 4 over the cosine of pi over 4. And those values we know. They are 1 over the square root of 2 and 1 over the square root of 2. Now, if you filled in that table, maybe you do know what the tangent of pi over 4 is, and that's great, that's fine. My point is that there are other ways to find them, and that these identities are going to come in very handy. So while this may seem like a very simple exercise, keep in mind that it may come in very handy in the future, and that the skill that we're developing here is an important one. Now, any number divided by itself is 1. So here I have 1. The numbers being this number and this number. Since they're the same, I'm dividing a number by itself. All right, let's try another one. Let's try the cosecant of 60 degrees. Well, I may not know offhand what the cosecant of 60 degrees is, but I do know that the cosecant is just 1 over the sine. So let's first rewrite this as 1 over the sine of 60 degrees. And I know what the sine of 60 degrees is. It's the square root of 3 over 2. If I write that as 1 over 1, that lets me rewrite this division problem as a multiplication problem. And I have that the cosecant of 60 degrees is 2 over the square root of 3. So that's how you can use these to evaluate functions other than sine and cosine. All right, let's take a look at what it means to simplify expressions using identities. Let's say I'm given the expression the cosecant of t over the secant of t. Let's see if we can simplify that. Well, we know the cosecant of t is 1 over sine, so let's rewrite the numerator as 1 over the sine of t. And we know that secant of t is 1 over cosine. So we'll rewrite that as well, 1 over cosine of t. Don't forget to use t when you're using those abbreviations. Now I have a fraction divided by a fraction, so I'm going to rewrite this as the numerator times the reciprocal of the denominator, and then I'm going to simplify and write as a single fraction. That's definitely simpler. Well, it's still a trigonometric function divided by a trigonometric function, but it's the two fundamental trigonometric functions. All right, but let's take a look at this. And on the right-hand side of my table, I have this exact expression. So that means I can simplify it even further as the cotangent of t. So I've taken this expression, which is a relationship between two trig functions, and simplified it down to 1. You'll be asked to do this with a variety of different expressions, but that's kind of how you do it. I'm going to use this idea now to show you some different ways to write one of our very important identities. And in fact, I should have included this in our list, so let me go ahead and do that. I'm going to add this to the list. And that is cosine squared plus sine squared, or sine squared plus cosine squared. You'll see it both ways. Equals 1. All right, that's a very important identity, and it's true for every value of t. Let's take that identity, I'm going to write it as sine squared of t plus cosine squared of t equals 1. And I'm going to divide both sides of this by the sine squared of t. Now, the left-hand side can be simplified or sort of broken down into sine squared over sine squared plus cosine squared over sine squared. In other words, if I gave you this pair of fractions with a common denominator and asked you to add them together, you would get this, the sum over the common denominator. Then I'm going to rewrite the right-hand side as 1 squared over sine squared. And then I'm going to rewrite the left-hand side. This is 1 plus, remember from algebra that a over b squared is equal to a squared over b squared. Well, here what I have is a squared over b squared. So I'm going to rewrite it as a over b all squared. And I'll do the same thing here. A squared over b squared is a over b all squared. Going to the next line, 1 stays 1. Recognizing that cosine over sine is, find it in here, just cotangent. Cosine over sine is cotangent. So I'm going to rewrite this as cotangent of t squared. And then, oops, that shouldn't be a plus there, that should be equals. Recognizing that 1 over sine is just cosecant, I can write this as cosecant of t. And on my last line, I'm just going to rewrite this using that other notation we have, cotangent squared and cosecant squared. And I have here another version, if you will, of what we call the Pythagorean identity. It's called the Pythagorean identity because it's based on the idea that x squared plus y squared equals r squared, all right? This is just a different version of that because it's taken from the original, and all I did was manipulate it a little bit. I'm going to add that to the bottom of my list here, but I'm not going to keep it in the box because I think of this as the primary primary Pythagorean identity, and this one and the other one that I'm going to show you are less common, I guess. They're just as important but less common, and you can always get those other two from this one. So I'll add this one and then I'll show you the other one, and we'll add that one to the list as well. So there's that one, and it's worth noting that you could also write this one as 1 equals cosecant squared of t minus cotangent squared of t, just by subtracting cotangent squared of t from both sides. So that's another form of the same formula, the same equation. I was going to show you the other one, but for two reasons I'm not. One reason is that I'm going to run out of time. I've run out of time as it is. The other reason is that I think that we should do that one in class. So I'm going to leave that other identity that's so closely related to this one for another time. The other things that we need to talk about in this subsection are how to use these identities to relate trigonometric functions, and to talk about the period of a function, and one or two other things as well. So this video is already getting rather longer than I wanted it to be. So let's kind of try to dive right back in here and pick up with the next idea. Some of the other things you can do with this information, some of the information that we have so far, is that, for example, if I give you that the sine of t is equal to, let's say, 7 over 13, and let's say that t is in quadrant 3, find, let's see, how about secant of t? Well, the easiest way, I think, to do this is to draw a quick sketch. I'm told that t is in quadrant 3, so I'm going to have an angle in quadrant 3. This is quadrant 3. I could draw a unit circle here. I don't really need one. I think I'll start out with not having a unit circle here, and then I'll add one later on if I remember to show you the difference. You can imagine a unit circle there. Anyway, so I know that the angle I'm interested in is in quadrant 3. So again, remember that the actual angle I'm working with here is this big one that starts on the positive x-axis and sweeps all the way through into quadrant 3. I also know that the sine of t is 7 over 13. And that based on the fact that this is a right triangle, I can say that the sine squared of t plus the cosine squared of t equals 1. But I know what the sine is. So if I rewrite this or rethink this as the sine of t squared plus the cosine of t squared equals 1. These notations, again, mean the same thing. This is just kind of our shorthand for, this is how most of the time how you'll see it presented, and it's most of the time how I would expect you to write the sine of t quantity squared. But this is what it means, and so it's fine to go back and forth between the two of these. The thing is, I've rewritten this way because I know what the sine of t is. It was given to me, so I can replace that sine of t with the value 7 over 13. Okay, and that is the sine is squared, so the 7 over 13 is squared. So I've rewritten it this way so that I can just replace the sine of t with 7 over 13. It's probably an unnecessary step for many of you, but just something to keep in mind. This gives me 49 over 169 That's 7 squared over 13 squared, plus, I wrote equals, I meant plus the cosine of t squared equals 1. And if I subtract 49 1/69 from both sides, I get the cosine of t squared equals 1 minus 49 over 169. And I'm going to write 1 as 169 over 169 because I need a common denominator so that I can do this arithmetic. And that gives me cosine of t all squared equals, the common denominator is 169. 169 minus 49 is 120. So the cosine of t, when you square it, gives you 120 over 169. So if I take the square root now, I get the cosine of t equals whatever the square root of 120 is over whatever the square root of 169 is. Well, that's 13, I know that. The square root of 120 can be reduced. Sorry, my pen stopped working. To 2 root 30 over 13. That does not further reduce. So I have found the cosine of t, but I wasn't asked for the cosine of t, I was asked for the secant of t. I find the secant of t is actually 1 over the cosine of t. So this fact implies that the secant of t is equal to the reciprocal, which is 13 over 2 root 30. And again, I don't care if you rationalize the denominator. This is perfectly acceptable as a final result. All right, there's one other concept in this subsection, and I'm not going to discuss it here. I will mention it so that we don't forget about it later on, and that is that of a period of a function. The period of a function is the amount of time it takes to go through one cycle and start over. So if you're looking at something on a unit circle, like the sine, then you want to think about what the sine value is at 0, what the sine value is all the way around until you get back to a coterminal angle. And once you start taking the sine of angles larger than 360 degrees, it's going to start repeating. The cycle will start repeating. So the cycle, or the period of a sine, is 360 degrees, or 2 pi. And that's what that means. We're going to spend a lot more time talking about period when we get to graphing. So that's all I want to do with that right now. I may discuss it a little bit more in class, but for our purposes for right now, that's going to suffice. The last thing your textbook talks about in this section is evaluating trigonometric functions with a calculator. And that, by all rights, should be its own video. It's a major subtopic. It's a major subsection of this section. But I'm not going to talk about it here because I don't really want you using a calculator. There is nothing wrong with using a calculator, and in fact, when I do trigonometry, I often do use a calculator. But I already know the underlying principles, and so I know when I use a calculator, if I get an answer that doesn't make sense, I will recognize that it doesn't make sense. If I asked you in 3rd grade to learn how to do division by using a calculator, you wouldn't understand what division really was. You would just understand which buttons to push. If you push the wrong button, you're not going to know. So I want you to learn how to do trigonometry without a calculator first, but yes, we will get to using a calculator, just not quite yet. So I'm not going to make a video about the last subsection, evaluating trigonometric functions with a calculator. We may, again, talk about it a little bit in class, but for the most part, you don't need to worry about that. I do hope you read it because I know you'll use a calculator for some of your work, but by and large, in class and on tests and things for right now, you'll be doing most of that work without a calculator. So that's going to do it for this video. I apologize, it's very long again, but hopefully we're going to get through these, and I'll just keep practicing making shorter videos. I do want the information in here to be enough to get you through the section. So I'll do my best without shortchanging you on the information. All right, I'll see you in the next section.